Can you hear us? Hi.
Hello.
Hello, Wesley.
Hi.
Okay, I think I'm being heard as the mic button is moving. Okay. You can get one from here. Just be careful. Okay, so it's already 5:36, so maybe we'll start and if other people come in. Okay, so welcome to the first session of reproducibility this semester. I don't know if some of you already know about the initiative. It's something that has started a while ago, and in Bordeaux it's being held. So it was first brought by Eduarda, and now it's being co-hosted by me as well. We're going to give you a short information. Mostly Eduarda is going to give a short information on what reproducibility is about, what the initiative has behind, and why we're interested in bringing this in Bordeaux, why we want this to continue.
We used it. No. Okay. So this initiative started in the UK, in Oxford, by these three students. They were PhDs back then, and they wanted to discuss on how to improve their research practices, and they were sort of struggling a bit with the PhD, so they also looked for like a safe space to talk about this experience. And they started with like a local journal club, which then became a podcast, and which is still available if you want to listen to. But the idea really was a lot of people liked it, and they started implementing in their own universities. So nowadays, the reproducibility is available in more than 139 institutions in more than 27 countries. And the idea is that they give you a framework, but you do locally, however suits you best. And as you can see here in the map, basically they are all over the place. And in France, there are some places. So now Bordeaux is also in the map, but a few other universities also have this initiative going on.
There's one in Lyon as well, but I don't know why it's not shown.
And here in Bordeaux, as you might know, the idea is that we will have monthly sessions. So once a month, usually the last Tuesday of the month, if there's no holidays. And it's article focused. So we usually bring a paper to be discussed. Someone is hosting the session and suggests a paper for others to read. It's a 15 to 20 minutes presentation. And then the rest of the session is for the discussion, which is supposed to be very informal and really it's like it to be a safe space among students. It's fine. So that's how we did it the previous semester. We had a good also like a lot of people per session, and now we are starting our next second semester now today. And we have different platforms online. So we have our Twitter, our OSF page, so the Open Science Framework page, where we keep most of the information, the calendar and what we are up to. The newsletter, so if you want to be informed about the next meetings, signing up the newsletter is the best way. And also we have an email if you have any questions or if you want to be part of the organization. Okay. And now today Fjola is opening the semester for presentation. So go ahead.
Yeah. Okay. So we already sent the paper for the presentation, what's going to be about. So it's the paper that was published by Benureau and Rougier. And we're going to speak a bit also about ReScience, which is, I don't know how many of you have heard of it, but it's a new journal that it's supposed to make people want to reproduce different models that have been published, but have not been published with their code, or have been published with their code, but still want to be replicated and to see if this model can be further used by scientists. Okay. So first of all, I think most of us are using code. Some are using it in a more computer science scenario, and some are using it in a more scientific scenario. But in the end, most scientists use code. And whereas software developers or people who come from a background that is of computer science have been taught the basis of writing code, some of them still don't respect everything about it. And whereas people who come from a more scientific background, like biology, myself, I come from medicine. So we weren't really taught to program in the way that is the most maybe adequate. So we learned more by trying. So what are the rules that we need to follow if we want to have code that is a real scientific contribution and not just something that gets us the result that we want, gets us the prestigious article at a paper, and then it's done, it cannot be replicated anymore. Some guy somewhere someday may say that we were a fraud because they cannot replicate the result because there's no code there. So how can we do something that can back us up for our future career and also help future researchers with what they're doing? Okay, so the 5 phases of transforming code into a scientific contribution are rerunning, repeating, reproducing, reusing, and replicating. So I'm going to go step by step with what each of them means. So this is a basic code. Most of you are pretty familiar with it. And people who are using Python here can directly see that this is not a code that you would actually write in Python 3, right? Because I don't know, can anyone tell me what's a bit wrong with this? Like here, what does this tell you? I mean, this is the code that runs, but not on Python 3, right? Okay. So everyone knows, I think, but no one wants to say anything. So this is a code that's normally suitable for Python. If I wanted to run this same code on a Python 3 console, because Python 2 has been lacking, I mean, starting from 2020, I think, will not be supported anymore. So everyone has had to switch to Python 3 now. So we won't be able to use this programming language anymore. So if I wanted to run this, I wouldn't be able to run it in my IDE or in my terminal if I have Python 3 installed. So what do I want to do? The first step is that I want to make this rerunnable. So this code that I have that generates me some result, I want to make it rerunnable to be able to make it run. I don't know, like when I press the run, I want it to do something. I don't want it to tell me that I have a syntax error. So first of all, I have to write what have I tested it for. So if someone wants to look at this code, if someone looks at this code, sees that it's Python 3, so he knows that he's going to use Python 3. Someday Python 4, I don't know, Python 5, I don't know if this is in the foreseeable future, but something like that may come up. And this may not be rerunnable in that either, but at least I'm writing that this was tested with Python 3. So everyone who knows the environment where I'm producing this code from. And then the code has been made more suitable for a Python 3 environment. I think this is lacking battery. Okay, so now I made it rerunnable. It's a bit different from the one that you see before, because first of all, just like the print statement, I have to change it. Now it's in parentheses. This is very basic coding. And I had to change also the append so that it makes it append to the list. I had to add a walk. So I made my code a bit longer, but this is just to make it run. Because I'm going to make it longer and longer. So now I want to make my code repeatable. So I want to be able to produce the same result that I produced the first time. So I ran this code. It gave me a result. And I want to repeat the same result that I got before. So what do I have to do for that is that I know that because I'm using a random generator, I have to set this up to a certain seed so that it gives me the same result. And then I want to print this result to see if I'm going to have the same result that I had before. So what I'm adding here is just I'm setting the seed and I'm just writing and I'm just printing the result and then writing it in a file so that I can compare it later. If I run the code again, will this give me the same result as before? So now I made it repeatable. Okay, so now this code is quite longer because now I want to make it also reproducible. So first of all, I started using functions here. I'm really sorry, I don't know what's going on. Okay, so first of all, I started using functions here. This is just to make it kind of prettier. So if I run this function, it's going to work. Then I also wrote who developed this, which version of Python it was run with, what operating system it was using, because sometimes if I want to use it in another operating system, it may introduce problems. So sometimes some of you may have heard of virtual machines or I don't know, Docker. So you have to be cautious with this as well. And then I have this thing, which is the Git control. So I say, if the repository is dirty, don't run anything. So I want to use version control or GitHub or Git. I don't know if you, I mean, most of you are computer scientists, so you know, but I hope everyone knows. So Git is a version control mechanism who tells you that your code is always, so how your code has progressed through time. So what this does is that in the moment that I'm running my codes today, I committed to Git, it's saved there in a version control. And the result that I get, I know that this result has actually come from this specific code. And tomorrow I'm going to change that code, right? Because I'm constantly developing my code. And now I want to know that the result that I got tomorrow may be different from the result that I get today. So I want to know what this result has come from. So here I'm telling it, if my repository is dirty, so if I don't have a commit, so if there is a changed file which has not been committed to Git, then don't let me run it. Because otherwise I want to know where this result has come from or why this result has come from. So I will have a result, but I won't be able to have the code that has given me this result. So first of all, this is the first step, and I find this really, really nice, as they mentioned in the paper. Then I send the hash, then I do unit testing. Some of you may have heard of different kinds of unit testing, or some use PyTest. So here I want to see if the same result that I got, so here I'm checking if the code is reproducible inside the code itself. So I'm running the code and I'm seeing if it's giving me the same result that I expect it to give me. So what essentially reproducibility, so to make a code reproducible, is the sum of all the three things, of all the things that we mentioned before. So we want to be able to rerun it, we want to be able to repeat it. So if I give it the same data that I gave it before, I want to receive the same result. Here I don't have any data, but if I give it the same commands, I want to have the same final random walk, right? I want to have the same, I want to have this numbers, right? So then I just run my code, and I'm saving my results. But if you pay attention here, I'm saving more results, I'm saving more information than the ones that I used to save before. So I'm also saving the data that I added, the seed, the time step that I'm looking at, the revision, and the system version that I was using, and then I'm writing the file. Okay. So this is what made my code reproducible. So if a scientist goes, when publishing a paper, wants to also publish his code with it. So there are papers now that have introduced this GitHub repository, like eLife has done this. So you can also use, so if you publish a paper and you have a code link to it, so you have a model, and you tell them that I have my GitHub repository and this is the code for the model that I published, they can fork your repository into theirs so that they can have your code there as well. So the moment that you have the paper, you can also access the code. But not every journal has this. This is very recent. But if a journal has this, then it means that you can just take their code and try to run it, and that would make it reproducible. Okay? And this is very helpful, right? Because sometimes you want to test if a model works just by yourself, just to see. It could be a learning experience for you, and you want to do this, but most of the times you don't have the code. So that's why it's good for scientists to also give the chance to give us the chance to reproduce our code. Okay. So the next step now is to make it reusable. So, okay, this scientist now published a paper. He has the code written somewhere. I'm supposed to use it. This code is just a random number generator, but let's say it's I want to pre-process fMRI data, like the IMN talk today, or I want to do this fancy deep learning algorithm, but I need some data for it. And my data is quite different from his. I have the code, I have everything, but it doesn't work. So what does this scientist, when creating this code and before publishing it into GitHub or before publishing it into the journal, has to do so that I'm freely able to use it? And the most important thing about this is documentation. So we want to have every step of that being clearly documented and clearly mentioned. Why have we done every step? Sometimes, I mean, I know it's really, for me, it's very hard to read other people's code, but sometimes even reading my own code not 2 days, 2 days is a bit of a stretch, but like 2 weeks later, if I haven't looked at it for 2 weeks, it may be a bit confusing. Like, why did I do this? So it's nice to always have documentation, not only for other people, but also to make your work more understandable. So this is something that we already saw. This is so we created this. The git hash is something we already saw. We computed the results, and now we have this written as two functions. And if we want to import this as a module, for example, we want to just import the functions and then run the functions if we need them. So that's why we use the if name is equal to main false. And so yeah, we want to mention everything that we're using and why we're using it, and to explain why every step is done so that the person who takes it next can be able to use it. So that would make it reusable. Sometimes, and that's also why it's important to mention the operating system, or if we want to be even more helpful and more generous to the people who are reading our code and really want them to be able to reuse our code, we shouldn't write our code in a specific OS, but we should like import it into as a virtual machine image, or we can put it into as a Docker image, so people from every operating system have access to it. Or we give them as well, so they can use it from the virtual machine. And the last step is replicability. So replicability may seem very similar to reproducibility, and sometimes it may be a bit obsolete into why we're using replicability if we have reproducibility. So if a scientist has already given me his code and I already have it and I can reuse it because he gave me all the information about it, why would I need to write it? Because replication would mean trying the same algorithm, but not necessarily the same code. So if a scientist has very clearly explained all the steps or has given me the code, I want to write something that does the same thing that he's supposed to do, but with a different algorithm, with a different way of writing it. And that's a great way of testing the code that he has. Because if I run the same code as him, and if it's reusable, then I may have the same errors. But if I know the algorithm that he's using, I have the general idea, the general framework, or even the code, and I say, okay, I'm going to use this, but I'm not going to 100% use the same code. I want to do something similar to this. Then I most probably won't run into the same errors because I'm creating different functions. I'm just taking his algorithm, right? So that's why reproducibility and replicability are not the same thing, but also to have a code that is reproducible and published, it's really good to help replicability, because I think most of us have tried to replicate code that was written or models that were published in papers. And sometimes there's quite a lot of problems with the way that they mention parameters. They're missing some things. They aren't always as accurate. You have to look a lot. Sometimes you have to send emails to the author, and that's not very helpful. But if the code is fully there, then you can easily grasp the algorithm of it and replicate it, right? Okay. So from another paper now, everything that we said, just a short summary of the 10 most important rules for replicability, and we'll be done. Okay, so for every result, keep track of how it was produced. So that was version control. That's why we wrote that if the repository is dirty, do not run this code. So that clause in the code forces me to always commit before I create a result. So that helps me with that. The second rule, avoid manual data manipulation steps. This is not very common when you're creating a model or in the code as such, but if you want to do EEG data analysis, sleep classification, fMRI studies, you always have this one step that you have to kind of do visually. You have to try to avoid that or create an automated system that does that for you, because that's very prone to human error and to subjectivity, and you cannot repeat that. Because I mean, if I do it a certain way and I judge it, and I judge something as a spindle, for example, someone else may not. So that's very problematic, and my algorithm would not work because I consider spindles a specific thing, and I know that there's a rule for it, but there's subjectivity to it, and I cannot replicate that. So the third one is archive the exact versions of all external programs used. This is very important, and we already did this in the code. Version control all custom scripts, which we do with Git. There are also other other environments that you can use to do this, but Git is the most used right now. Record all intermediate results when possible in standardized format. So you can do this in the form of a debugger that whenever you run your code, it prints some of the results. So you can make sure that it's running the proper way, or you have something to check. Okay. For analyzers that include randomness, note underlying random seeds, which we did. We set the seed. Always store raw data behind plot. So you always want to say which data has produced that plot. Generate hierarchical analysis output and layers of increasing detail to be inspected. This is also very important. Textual statements are the documentation that we set. I think this codes were very little documented, but this is perfect still because most code isn't. But if you want to, Spider or some IDEs have an option that you write the information of what the function does, but you can also write the parameters that you're entering and what it returns, and you can write what type it is and what that exactly means. So you can also incorporate that in your code if you find it interesting. And I think that's very helpful for people to read your code. And provide public access to scripts, runs, and results. And this is something that I've noticed that with yours, fortunately, has changed. And we were just discussing a bit about this because computer engineers before thought that considered code as a very private thing. Software engineers is a very private thing, which was a work of art that they had created themselves. But fortunately, with time, this has changed and hopefully scientists will do this even more than they do already. So all this presentation was actually inspired by this challenge. I don't know if you've heard about it. It's in IMN for the people who are there. It's somewhere hanging in one of the walls. So it's the 10-year reproducibility challenge. So it's sent to all scientists if they can reproduce a code that was written by them 10 years ago. And it may sound easy when you first hear it, but sometimes even when you want to reproduce the code that you've written a year ago, it's pretty hard, especially if you haven't followed these steps, it's pretty hard. And 10 years ago means that you probably used Python 2 or some other languages like, I don't know, Pascal or Mathematica, which are languages that currently are not being used anymore, are almost dead. I don't know if I should say that, but okay. And then, so yeah, this was a bit of an explanation of what this is. And I think from the people who tried to publish to this and then to the ReScience, I think 13 publications, 13 people managed to replicate their code, if I'm not mistaken, yes. Then, starting from this, the ReScience organization and the ReScience journal started. And the purpose of this journal is to start something that scientists try to replicate code that was previously found on another paper but has not been published. So for example, there's a very important paper published in Nature somewhere or in Brain or I don't know, neuroimaging or somewhere, and you find it really interesting and you want to replicate it. So you can do this by yourself just to see if it gives you the same result, or even if you want to use it because it has shown to be a great model or a great algorithm. So if you replicate it and you want to publish it so that other people like you don't have to go through all the 6 or 8 or 9 months of trying to do the same code, then this is a great option to do it. The first paper that was published here was actually a paper that was done from people inside our lab, and it was something that was written in Pascal, I think, or Java, I don't remember, but it took them just 4 months to replicate something that so just the first author of the paper was not in the lab, but 2 other people were in the lab, and it took them still 4 months to be able to replicate this code. And that's like so strenuous. And if you imagine all other people trying to do the same thing, them publishing this code is a huge help to everyone. And also, I think most master students, but also quite a lot of PhD students, when we learn new models and we try to understand them properly, we replicate these models. So why not have a publication out of this, right? So that's why I think this is a great idea. There are a lot of people who may be opposed to this, so this remains for discussion because it takes a lot of time to replicate a model. So some people may be like, I don't want to waste time to replicate this model fully. I want to I don't know, I want to build something that gives me a paper in Nature, not in ReScience. So, and one other thing that I want to share with you, which I found really interesting, and I think it's a very good discussion point, is something that the ReScience journal suggested. So at the moment, what they're doing is this author that published in Nature has this publication, and then this author B goes and checks this publication, reads it and everything, and wants to replicate it, properly replicates it, and then gives feedback to the author and the editor, and then publishes it in ReScience, right? So this is what's happening now with ReScience. And if it's not replicable, then people don't really want to publish because they don't want to have problems with people who have published in Nature. So so far there have been no replication failure publications. But what they suggested, which I find pretty interesting, is that they wanted to have, like, if authors from group A want to publish something and have a model, they share this with so they send it to the journal, and then authors from another group B, which is irrelated to group A, but who does computational work and does all these things, similar things, tries to replicate the model that they have mentioned in their paper. And if they manage to replicate it successfully, then the article gets published. So that's why it's called co-science. And it's interesting. I don't know how feasible it is, but yeah, worthy of discussion. So thank you for your attention, and write replicable and reproducible code. Yes.
Thank you for. I didn't quite understand the co-science.
Oh, okay. Let me go through it again. Okay. So let's say you're from Nemozin, right? And I don't know, who are the other teams here? Can you give me a name of another? Yes. What's the name? Wagner's Lab. Yeah. So our group, Nemozin group, writes a paper, and it has a model, the model that you introduced today, the hippocampus model. And we send it to the journal, and the journal say, okay, before I publish your model, I'm going to check with Wagner's group. They're going to see if they can replicate your model. And if they can replicate your model, then your model is publishable. It's good to be published. So then both of you are going to be authors, but of course, I mean, the value of your authorship is going to be, like, you're going to be among the first authors, and it's going to be explained how much contribution each had, but both of you are going to be authors. So this check that we do after, if the model is replicable, is going to be done before you publish.
It's like a kind of peer review, but there's
Exactly. Yeah.
But do you think that can be biased sometimes?
Mm.
Well, it's like
How
peer,
so?
it's like peer review can be biased.
Yeah.
Yeah.
So you would have the same.
If
So
it's
you
a-
would probably
at
want to have
least
3 or
small
4
lines.
people replicating the code.
Yeah. That would be a lot, because replicating a model takes quite a lot of time. But again, if you have it reproducible and you provide the code, then it may take less. So you could have 2 groups. But the idea now is just to have one group at least.
So the product, does this already exist?
No.
Is this gonna be an extension to ReScience, or?
This
whose
was
idea?
a suggestion that they mentioned in the paper that they introduced to ReScience in 2018, and they are suggesting it, but I think it's a long way there. So, something that's going to be in the future, but it's a curious thing, and it's interesting to also know what people think if this is.
By replicating, you mean that, so you're going to provide a paper, you're going to provide a code also.
Okay, so they can do both. So remember when I said that reproducibility helps replicability? So so having something that's reproducible, meaning it means that I will give you my code, my full code, and then I tell you, can you replicate it? The other way is that I give you very clear instructions on how the model works, and then you try to replicate it. So it can be both, but I think with an initiative as co-science, it would probably be the first that you provide the code as well. But not that they have to, but that they run the same code.
So they have to write a code that is the same.
Yeah, exactly. But with the same algorithm.
So it's
that you
just,
have.
yeah. My point about having different groups is that hence you will be maybe too reliable to the skills of the